Hi, Jordan here. Welcome back to my channel and the second video in my series on the Schauberger double spiral flow pipes. Today I'm going to discuss a little bit about forms and formula. So, this is a double spiral flow pipe. It is cast in wax, coated in copper paint. It measures 28 inches from end to end using a sewing measuring tape, and it has a surface area of about 200 square inches. This is the plating math that I'll be using. So in order to determine the thickness of copper that will plate on the part over a given period of time, I use these three steps. First, calculate the quantity of charge using the amperage and time. So I have a 25 amp rectifier. If I apply 25 amps over 1 day, 86,400 seconds, I get 2,162,500 coulombs. Second step is to calculate the number of moles of electrons. And to do that, take the quantity calculated in the first step divided by Faraday's constant, 96,500 coulombs per mole. That yields a result of 22.4 moles. So now, using stoichiometry, determine the number of moles of electrons. Many other people can explain this much better on the internet. I'm not trained as a chemist. I've learned all this through books and YouTube. So, using stoichiometry, determine the number of moles of copper that we'll need, 40 moles of copper. Now, to determine the mass, take the molar mass of copper, 63.5 grams per mole. And to determine the mass, we multiply the number of moles of copper by the molar mass. And that's 40 moles of copper by 63.5 grams per mole yields 2,540 grams of copper, which is approximately 90 ounces. And I found this calculation online. I'm not sure. I will only know through experimentation if this is true, but if you take 1 ounce of copper spread over 1 square foot, or 144 square inches, so assume this is 144 square inches for the sake of making the math simple. So 1 ounce over 144 square inches will give 1.37 thousandths of an inch. So if I take the 90 ounces that I'm going to deposit over the surface area of this part, I get 90 by 0.00137 gives me 0.1233 inches, which is approximately 1/8 of an inch, which is approximately the wall thickness I'm aiming for on this part. So that is the math to determine the copper deposition. This is a small plating test. What I do is I take my solution, drop it into a beaker, plate, peel the copper off, and if the copper has the qualities I'm looking for, ductility, fine grain structure, smoothness, then I'm ready to load the part in the bath. And that's where I am right now. So the formulation I'm using is the Clifton Phillips Bright formulation. It is 26.5 ounces per gallon of copper sulfate, sulfuric acid 4 ounces per gallon, chloride at 50 to 120 ounces per gallon, urea at 0.005 ounces per gallon, and molasses at 0.1 ounce per gallon. So that's the formula. These chemicals, you don't need to use sulfuric acid, pure reagent grade sulfuric acid, or hydrogen chloride. You can use drain cleaner. I've used drain cleaner before. Instead of copper sulfate, I've used root kill. And first form I made, which is the original for this one, I used a very simple formulation. So, to make the parts, I use these two boilers. These are 30 liters each, and one is filled with a blend of waxes, the other is filled with water. So when I'm in the process of making the wax forms, the wax is melted to 80 degrees Celsius. It is a blend of waxes specially engineered for hockey arenas, and it has characteristics. It's ideal for this process. Yeah, I used candle wax in the beginning, and when I extracted the part, it cracked up. So, blend of waxes, heated to 80 degrees Celsius, and I have a special process for actually creating these, which will be the topic of a separate video. But in simple terms, what I do is fill the horn up with wax, let it cool, dip it in boiling water, and extract the form. And then I modify that form to what you see here on the table. To get the spiral groove, I half carve and half melt it out, starting at the top and melting it out such that the wax flows through the groove and does not alter the surface texture of the rest of the part. So a blend of waxes, boiling water. You don't need to use this special equipment. When I started, I was using a bunch of tomato sauce cans, all soldered together. So I'd fill this up with hot water and flash the copper horn filled with wax to extract the cast, to extract the wax form. So there it is. That's the math. I'm all ready to load the part. Some of the books that I've been using: Electroforming by Leslie Curtis. This was a very good book. Jason Welsh, Electroforming for Beginners. His YouTube channel is what got me started in all of this. This is one of the first repulsine turbines that I made, and it's made of copper. The nozzles are auger seashells, and it does produce a very cool stream of air. This would be the topic of a separate video. This is a failed double spiral flow pipe. The copper was very poor quality, and from the failures I've learned a lot. Some ceramics that have been electrotyped. These ones need to be polished. Okay, so in the next video, I'm going to go over to the tanks, load the anodes, and discuss a little bit about the tank construction and how the anode is loaded, how I integrate the slip coupling onto the cathode, such that the part can rotate within the bath. Okay. Metal Finishing Handbook, Universal Metal Finishing Handbook. This you can find on academia.edu, and I have this printed and bound. This book is invaluable, as is Volume 5 of the Metal Finishing Handbook, and of course all the Schauberger literature, which I reference occasionally, but I have lots of this memorized. And what am I building here? So there's a repulsine, and there's my interpretation of a repulsine. The bottom, it's all copper. So the process for this, you have a template, electroform that, and then put a resist like wax or latex, paint more copper, electroform it again to create the bottom and top plates. So the process is very well suited for replicating this technology, and we'll see what happens.